What is the universe made of? This question has been a source of wonder and curiosity for as long as humanity has existed. From the earliest civilizations to the modern age, we have looked up at the night sky and pondered our place in the cosmos. This question has captivated philosophers and scientists for millennia. Ancient thinkers like Aristotle and Democritus debated the nature of matter, while modern scientists continue to explore the depths of this profound mystery. We gaze at the stars vast and distant and wonder about the fundamental building blocks of reality. The night sky with its countless stars and galaxies serves as a constant reminder of the vastness and complexity of the universe. While classical physics elegantly describes the motion of planets and the laws governing everyday objects, it provides a framework that has stood the test of time. Newton's laws of motion and gravity explain much of what we observe in our daily lives and the movements of celestial bodies. However, it falters when we delve into the realm of the very small, the world of atoms and subatomic particles. At this scale, the rules of classical physics no longer apply, and a new set of principles is needed to understand the behavior of matter. This is where quantum mechanics takes center stage, revealing a universe stranger and more wondrous than we ever imagined. Quantum mechanics introduces concepts that challenge our everyday experiences and intuitions, offering a glimpse into a hidden world. Imagine a world where energy doesn't flow smoothly but exists in discrete packets, like tiny bundles of light. These packets, known as quanta, form the basis of quantum theory and revolutionize our understanding of energy and matter. Picture particles behaving like waves, rippling through space, their positions and speeds shrouded in a fundamental uncertainty. This wave-particle duality is one of the most intriguing aspects of quantum mechanics, blurring the line between particles and waves. This is the captivating realm of quantum mechanics, a theory that has revolutionized our understanding of the universe and paved the way for groundbreaking technologies. Quantum mechanics has led to the development of technologies such as quantum computers, which have the potential to solve problems that are currently beyond the reach of classical computers. Our journey into the quantum realm begins at the turn of the 20th century with a German physicist named Max Planck, whose work laid the foundation for this revolutionary field of study. Max Planck would forever alter the course of scientific thought. His introduction of the quantum hypothesis marked the beginning of a new era in physics, challenging the established notions of energy and matter. His groundbreaking work on blackbody radiation, seemingly a niche area of study, would unlock the door to a hidden universe governed by astonishing rules. Planck's work demonstrated that energy is quantized, a concept that would become a cornerstone of quantum theory. Fasten your seatbelts, as we are about to embark on a thrilling adventure through the quantum realm. This journey will take us through the strange and fascinating world of quantum mechanics, where the rules of classical physics are turned on their head and new possibilities emerge. The year 1900 marked not only the dawn of a new century, but also a revolution in physics. It was a time of great change and discovery, where the boundaries of scientific knowledge were being pushed to their limits. Max Planck, a German theoretical physicist, while studying the perplexing problem of blackbody radiation, found himself on the brink of a groundbreaking discovery. He stumbled upon a radical idea that would lay the foundation for quantum mechanics, a field that would revolutionize our understanding of the microscopic world. Classical physics, the stalwart of scientific thought for centuries, had provided a framework for understanding the natural world. It was based on the idea that energy and matter were continuous and could be divided infinitely. According to classical physics, the energy emitted by a heated object should increase infinitely as the frequency of radiation increased. This was known as the ultraviolet catastrophe. Yet, experimental observations stubbornly refused to comply. The data showed that the energy emitted by a blackbody did not increase infinitely, but instead reached a peak and then decreased. Planck, in a stroke of genius, proposed that energy was not emitted continuously, but rather in discrete packets, which he called quanta. This was a revolutionary idea that challenged the very foundations of classical physics. Imagine a vending machine that only dispenses coins in specific denominations like quarters or dimes, instead of allowing you to insert any amount. This analogy helps to understand Planck's concept of quantized energy. Similarly, Planck suggested that energy could only exist in multiples of a fundamental unit, now known as Planck's constant, denoted by the letter chi. This constant is incredibly small, but it has profound implications for the behavior of particles at the quantum level. This revolutionary idea, though seemingly simple, had profound implications. It meant that the energy levels of atoms and molecules were quantized, leading to the development of quantum mechanics. It meant that energy was quantized, meaning it could only take on specific discrete values. This was a radical departure from classical physics, which assumed energy to be continuous and infinitely divisible. This was a radical departure from classical physics, which assumed energy to be continuous and infinitely divisible. The quantization of energy led to a new understanding of the behavior of particles at the atomic and subatomic levels. Planck himself was initially hesitant about the full implications of his proposal. He viewed his idea as a mathematical trick rather than a fundamental change in our understanding of nature. But little did he know that he had opened Pandora's box, unleashing a cascade of discoveries that would redefine our understanding of the universe. His work paved the way for the development of quantum mechanics, a field that has led to countless technological advancements and a deeper understanding of the fundamental nature of reality. Today, the principles of quantum mechanics are at the heart of many modern technologies, from semiconductors and lasers to quantum computers and cryptography. Planck's discovery of energy quanta was the first step on a journey that continues to this day, as scientists explore the mysteries of the quantum world. The concept of energy coming in packets has not only changed the way we understand the universe, but also how we interact with it. It has opened up new possibilities and challenges, pushing the boundaries of what we can achieve with science and technology. Max Planck's revolutionary idea of energy quanta remains one of the most significant milestones in the history of science, a testament to the power of human curiosity and the relentless pursuit of knowledge. While Planck's quantum hypothesis initially met with skepticism, it wasn't long before its explanatory power became undeniable. Planck's idea that energy is quantized, meaning it comes in discrete packets rather than a continuous flow, was revolutionary. It challenged the classical physics of the time, which treated energy as a smooth, unbroken wave. This new perspective opened up a world of possibilities and set the stage for future discoveries in the realm of quantum mechanics. In 1905, Albert Einstein, a young patent clerk with a penchant for revolutionary ideas, seized upon Planck's concept of quantized energy to explain a perplexing phenomenon known as the photoelectric effect. Einstein was working in a patent office in Bern, Switzerland, but his mind was constantly buzzing with scientific inquiries. He was particularly intrigued by the way light interacted with matter, a topic that had puzzled scientists for years. The photoelectric effect, simply put, is the emission of electrons from a material when light shines upon it. When light hits a material, it can cause electrons to be ejected from the surface of that material. This phenomenon was observed in various experiments, but the results were baffling and seemed to defy the existing laws of physics. What puzzled scientists was that the energy of the emitted electrons depended not on the intensity of the light, as classical physics predicted, but rather on its frequency. According to classical wave theory, increasing the light's intensity should increase the energy of the emitted electrons. However, experiments showed that only the frequency of the light mattered. Low-frequency light, no matter how intense, failed to eject electrons, while high-frequency light, even at low intensities, succeeded. This was a baffling observation that classical physics simply couldn't explain. The wave theory of light, which had been widely accepted, was unable to account for these experimental results. Scientists were left scratching their heads, searching for a new explanation that could reconcile these findings with the known laws of physics. Einstein, with his characteristic brilliance, proposed that light too was quantized. He suggested that light could be thought of as consisting of particles, or quanta, of energy. This was a radical departure from the traditional wave theory and required a complete rethinking of the nature of light. He envisioned light not merely as a wave, but as a stream of discrete energy packets, which he called photons. Each photon carried a specific amount of energy, proportional to the frequency of the light. This idea provided a new way to understand the interaction between light and matter. These photons, carrying energy proportional to their frequency, could transfer their energy to electrons within the material, ejecting them if the energy was sufficient to overcome the binding force holding the electrons to the material. This explained why only light of a certain frequency could cause electron emission. The photons needed enough energy to free the electrons from their atomic bonds. Einstein's explanation of the photoelectric effect, firmly rooted in Planck's quantum hypothesis, earned him the 1921 Nobel Prize in Physics and solidified the concept of light quanta as a cornerstone of quantum theory. This groundbreaking work not only advanced our understanding of light and energy, but also paved the way for the development of quantum mechanics, a field that continues to revolutionize science and technology to this day. Section 4. The duality dilemma, wave or particle. The early 20th century witnessed a tug-of-war in the world of physics. Light, long considered a wave, now exhibited particle-like behavior thanks to Einstein's explanation of the photoelectric effect. But the story doesn't end there. In a surprising twist, particles, those tiny building blocks of matter, were about to reveal their own wave-like nature. In 1924, Louis de Broglie, a French physicist, put forth a bold hypothesis. He proposed that just as light, a wave, could exhibit particle-like properties, particles too could possess wave-like characteristics. De Broglie's hypothesis, though radical at the time, was soon confirmed by experiments demonstrating the diffraction of electrons, a phenomenon previously associated only with waves. This wave-particle duality, as it came to be known, shattered the classical view of a clear distinction between waves and particles. It became apparent that the subatomic world danced to a different tune, one where entities could exhibit both wave-like and particle-like properties depending on the experimental setup. This counterintuitive concept, though challenging to grasp, lies at the heart of quantum mechanics. Section 5. Heisenberg's uncertainty, a fundamental limit to knowledge. The wave-particle duality introduced a profound shift in our understanding of the subatomic world, but the strangeness of quantum mechanics doesn't end there. In 1927, German physicist Werner Heisenberg unveiled another startling aspect of the quantum realm, the uncertainty principle. Heisenberg's uncertainty principle states that there are fundamental limits to the precision with which certain pairs of physical properties, such as position and momentum, can be simultaneously known. It's not a matter of our measurement tools being inadequate. Rather, it's an inherent property of nature, woven into the fabric of the quantum world. Imagine trying to pinpoint the exact location and speed of a tiny, fast-moving particle. The very act of measuring its position, perhaps by bouncing a photon off of it, inevitably disturbs its momentum, making it impossible to know both with perfect accuracy. The more precisely we try to determine one, the more the other becomes uncertain. This inherent uncertainty isn't a reflection of our ignorance, but a fundamental characteristic of the quantum world. A world where certainty gives way to probabilities and potentialities.